Sarvesh, if you want the AC to be reduced or something, the remote is over here.
Okay. So far, so good. Okay, so welcome back, everybody. So we're happy to have Gautam Aishwarya from the Technion, and we'll be speaking about displacement convexity.
Talk about displacement convexity of entropy to some geometric and functional inequalities.
Just click once on the slide and then it should go. Now it should.
So I will just in the first slide show some sample results, the kind of things that I'll prove for you today. So for example, this is a Brunn Minkowski type inequality for the Gaussian measure.
This is the corollary of what?
Something that we'll see later. And so here this is for star-shaped compact sets, which I will define later what they are. And you cannot expect something like this for all compact sets, as we will see later. And the main innovation over here is that the convexity of the admissible sets is not needed. So this is the main idea here.
Is scaling kind of an issue? 1 over 2 to the n. So these K0, these are bodies in R to the n.
Yes.
And the exponent is 1 over 2 to the n.
Yes. So I'll get into all these things. Yes.
Oh, that is Gaussian.
Yeah. So this is Gaussian. And then the second thing is, if you look at the Ornstein-Uhlenbeck semigroups, and then we get some bounds for convergence of even log-concave initial data. So this is something else. And we'll define all these things as they come. And the main thing over here is that we can do this if we restrict to even log-concave functions. We can do this with a better convergence rate than the usual one. So these are the two types of results that I want to talk about today. And these two things are corollaries. And the main idea behind both of these things is convexity properties of relative entropy along optimal transport. So this will be the unifying thing. And so for geometry, that is the Gaussian, Brunn Minkowski inequalities and things like this, I would like to think of the measure, like the Gaussian measure, as some kind of maximum entropy. So if I prove some concavity property of entropy, it translates into concavity properties of the measure. This is the underlying idea for the geometry part. And this I will present on slides. Hopefully, I'll completely present what I want to present.
When you say maximum entropy, like a maximum entropy distribution under some constraint.
So I will, for example, volume is the maximum, the log volume is maximum Shannon-Boltzmann entropy, like that. Okay. And we'll see all these things more precisely later. And the second thing is for functional inequalities, one can think of, and again, we don't have to think about these terms right now, the heat flow as the gradient flow of relative entropy. So the heat flow corresponding to any reference measure can be thought of as the gradient flow of relative entropy. So in Rn, if you have a convex function and you're looking at its gradient flow, if you can show that the function is more convex, then the convergence to equilibrium will be faster. It will fall into the hole faster. So this is the underlying idea behind the second part. So in particular, I want to talk about the logarithmic Sobolev inequality. And this would be on the board if I manage to completely finish this in reasonable time. So now we'll start with some nice warm-up. So we have seen the Brunn Minkowski inequality earlier today. So this Brunn Minkowski inequality was in Elizabeth's talk earlier. It's the same thing. Here I write this in terms of 1 minus t and t, but if you just let, in morning's talk, if you just let this be this and this be this, because volume scales like t to the power n. Right?
K1.
Thank you. Because volume scales like t to the power n, so this thing, whatever on the board, is the same thing as this, which appeared earlier. Okay. And so this is saying that the volume measure, the Lebesgue measure, is 1 over n concave. This is what this is saying, in some sense. And now, by scaling properties of volume, again some tricks and this and that, you can show that this is actually equivalent to this weaker geometric form. So the stronger form, of course, implies this weaker form by the AMGM inequality. This is the arithmetic mean and this is the geometric mean. So this is a priori weaker, but for volume, these two things are equivalent. So as warm-up, I'm going to try to prove this using entropy. And let's see how to do that. Okay, so the first step is to find a natural notion of entropy, because I just said entropy as a vague thing. So I need to find the notion of entropy to encode volume. And this would be given to me by the Shannon-Boltzmann entropy. So let mu be a probability measure with density on Rn. Say its density is F. Then the entropy is given by this formula, the Boltzmann formula, or whatever, integral minus F log F. So this is entropy. And now if mu does not have density, you can set it to be minus infinity. And later we'll see why this definition kind of makes sense. And please feel free to ask me questions at any point. And sometimes I'll write h of f, even though here I have written h of mu. Sometimes I'll write h of x if x is a random vector which has the distribution mu and so on. And this is a measure, like all notions of entropy should be, a measure of how spread out the distribution is. If the distribution is more spread out, its entropy is more. Any questions? So now this is how we will encode volume. That if I fix a compact set K, I look at entropies of all the random vectors supported on it, all the probability measures supported on it. The maximum entropy that can exist on a compact set is the log volume. And the proof is extremely simple. So if X has density F, then this is simply the formula for entropy, which I can write like an expectation. And then I can use Jensen's inequality to pull out the logarithm and then just calculate. So it's very simple. And just from this use of Jensen's inequality, you can see that equality is attained if and only if X is uniformly distributed on K. So the uniform measure attains maximum entropy, and this maximum entropy is log volume. Okay, so now we have step one is done. We have some notion of entropy to encode volume, and now if I want to prove this inequality, this is the multiplicative version. So I'll prove for you the multiplicative version of Brunn Minkowski. I just took the log. So this is like this. So what do I need to do? What I can do is, if I can show, I know that log volume is maximum entropy. So if for every measure mu naught on k naught and every measure mu1 on k1, if I can find an interpolating measure on this geometric, not geometric, but the geometric arithmetic average, this Minkowski sum, if I can find an interpolating measure on this such that its entropy is more than the thing on the right, I would be done. I could just take supremums throughout and I would get the Brunn Minkowski inequality. So now I need to find out a suitable interpolation which does this, such that mu t is supported on this Minkowski sum. So let's see how to find this interpolation. And so I want to think of gases. So suppose this is a gas, this is a configuration of a gas. So I'm trying to think of probability measures as configurations of gases, right? So if there's more molecules in a unit area, the density is more and that sort of a thing. So I have a gas which occupies a region K naught, and I have another configuration of the same gas which occupies this region K1. So these are molecules, and they are like, in my picture, it looks like they are uniformly distributed. Because, yeah. Now, this is what we did. Now I want to look at all vector fields, time-dependent vector fields, all winds which displace this configuration at time t is equal to 0 to this configuration at time t is equal to 1. I want to look at all time-dependent vector fields, all winds which achieve this. So if you give me a vector field, a time-dependent vector field, which does this, then so the time-dependent vector field is flowing, the gas is displacing. At any time I can stop and I can look at the configuration. and that would, I would call that mu t at the intermediate stage. And now I want to pick, so like in physics, you minimize action. I want to pick that displacement, which is that choice of time-dependent vector field, which minimizes the average kinetic energy. So this is the one that I pick. And mu t is the intermediate distribution at time t along this flow, which we discussed earlier. So any questions about the previous picture? Be happy to go back to it.
So is there an evaluation equation which describes this?
Yes. This is what this is optimal transfer. This is what we'll get to. So this interpolating mu t corresponding to the optimal vector field, this is called a displacement interpolation. So I have a way to interpolate between configurations of gases, and the optimal one, the one which minimizes action, is called displacement interpolation. And it turns out that the optimal vector field is a gradient field. And it's not surprising, because you can split a vector field into two components, and the rotational part will not do anything. It will not move stuff. So the optimal one is a gradient field, and what it does is it moves each molecule from this to its final destination along a straight line. This is what it does. So I move everything along a straight line. So if this was k0 and this was k1, then whatever these molecules are at time t, this would be something which is contained in the set of all t midpoints, which is precisely the Minkowski sum. So the interpolation, by virtue of traveling along straight lines for each molecule with constant speed, is supported inside the Minkowski sum. And and this is something, so the measure evolves according to the vector field grad theta t. So this is some equation, the continuity equation, like the conservation of mass, that if this allows you to differentiate any given function along this flow. So the amount of mass that changes is equal to the flux. So this is one equation that you get. This equation has nothing to do with optimality. So whenever you would have an evolution of a measure, a gas, along a vector field, that vector field would satisfy this property.
Is it obvious that that theta t is the one, I mean the straight line one is the optimal one?
No. As from, at least from the things that I've said now.
The left side of the equation, I mean the right side, it's some sort of action, or what does that mean?
So the right side is I interpret this as like the flux. So I'm interpreting this as mass against this measure. So I'm just writing explicitly what sometimes is written in this manner. And this would make sense if everything has density, nice densities, and so on. Vt. Just writing down this equation.
Like what?
Yes. So this would hold for anything. The second one, on the other hand, is something to do with optimality. So the velocity field satisfies this Hamilton-Jacobi equation. So what we have just described, is the Eulerian description of optimal transport. So when people try to describe optimal transport, this is not the first picture that they sketch. But for us, this will kind of be more important. So right now, what we have done is we have taken the viewpoint of vector fields. The gas was displacing, the molecules were moving. We sat down at one point in space and we watched them move. And now I will discuss optimal transport in a little more generality, and then focus on the viewpoint of each particle. This is the Eulerian viewpoint, and that would be the so-called Lagrangian viewpoint. So now it will be a quick introduction to optimal transport. So this can be done in very general situations. I have x and y are Polish spaces, and I have a lower semi-continuous function, which is supposed to be a cost function. I have a lower semi-continuous cost function. And then the problem is that if you give me probability measures mu on x and mu on y, I want to minimize the total cost over all couplings pi of mu and nu. This is the statement of the optimal transport problem with cost c.
How you define couplings?
So coupling would be a probability measure on the product space which satisfies these properties. And we'll get to a more descriptive description of couplings in a minute. So this is just the formal definition of a coupling. It's a joint distribution. Coupling is a joint distribution. So why is this called optimal transport? Because the picture that is usually drawn is better than this. But so there's so I wanted this to be a pile of sand and I wanted this to be a hole, but I shifted this. So let this be a pile. Let this be sand inside a hole, and I want to move this sand here. So the distribution of the sand particles is according to the measure mu. So the total mass of the sand is 1, and mu tells you where it can at this point can contain more mass and things like this. And I want to move this sand to this pile here, this pile of sand here, and nu tells me how much sand I can fit in at a particular point. And d pi x comma y, the coupling, tells me the amount of sand I want to pick up from x and drop at y. So this is an infinitesimal amount because these measures are not discrete and so on. So I pick up some sand and I put them at y. And the cost for this movement is cx comma y. So I want to minimize the total cost. From here you can also see those formulas that I wrote over there. That if I want to see, if I fix a region A over here, and I look at all the sand that I have picked from here and dumped wherever, this should be equal to the total mass of sand that is present here. So that's mu A and nu B similarly. Okay. So any questions about this? So some nice cases that everyone likes is when both these Polish spaces are the same metric space, and that you're looking at is distance squared. So this is a very good example. And in this case, the total cost, like the optimal cost given to probability measures mu and nu, if you take the square root, is a metric on the space of probability measures with finite second moments. So this is called the Wasserstein metric. And the space of probability measures with this metric is called the 2 Wasserstein space. And you could have done a P over here and a P over here, and then you would get a P Wasserstein space, and so on. And this satisfies nice properties. So if X is a geodesic space, meaning that any 2 points in X can be connected by a distance achieving path. And I don't write it because we not really need it other than intuitively understanding it. If X is a geodesic space, then this Wasserstein space is also a geodesic space. Moreover, the convexity of entropy, which I have not defined which entropy here, the convexity of entropy on this space along the geodesics can be used to define Ricci curvature lower bounds. So for example, if you had a Riemannian manifold, and this was your Riemannian metric, like the metric coming from the Riemannian metric, right? And if you did minus f log f or f log f type things with respect to the volume measure, then the condition of the Ricci curvature bounded below by k is equivalent to the k convexity of entropy. So, so this is true, and this idea can be used to define spaces where there is no smooth structure. Like you can have a geodesic space and a measure on it. You can define what it means to say that the Ricci curvature of this metric measure space is bounded below by k. So, any questions?
We're doing, but one thing is that in this way of defining, it's like kind of a global definition of Ricci curvature or lower bound.
Yes.
You cannot do a pointwise like in the differential geometry.
This is true. Yes. This is, and I'm sure that there may be. Yes, we can construct things which do things locally because your space is isometrically sitting inside Wasserstein space by the uninteresting Dirac masses. So, in principle, yes, but I don't think there's any interesting way of looking at it yet. So, the second example is that you can take a strictly convex function and you can take this to be the cost, Rn. This is the second example. So let us go. Yes. Let us go back to Euclidean space and our quadratic cost. And so if the source measure has density, then so I was talking about couplings, right? So this allows you to divide mass. But if mu has density, you don't have to do that. You can achieve optimal transport via deterministic maps. So if you find me a map T which pushes forward mu naught to mu 1, this automatically gives you a coupling. And in the Euclidean case, if your source measure has density, it is sufficient to look at such couplings. And it was proved by Brunn originally and then refined by McCann that this minimum is uniquely attained by the gradient of a convex function. This thing is super important. If someone in the audience would treat this as an introductory talk on optimal transport, and if they want to remember one thing from it, then it is this: that if you have a
5 or 5.
Oh, sorry, 5. Whichever, the same or both. 5. So So basically what I'm saying is that if you have a random vector x which has density on Rn, if you have any other random vector y, you can write y as grad phi x. This is what I'm saying. I'm saying that x has density, y is anything. You can always write y as grad phi x for some convex function phi. So this is called the Brunn map.
Is it in some dual space or looking the map?
So why do you say?
Because grad phi acting over, because x is a random vector, right?
Mhm.
It's an action.
It's a very good point. Yes, I like thinking about it in this way, but I often confuse myself when I do such a thing. So here I just mean grad phi is a map from Rn to Rn. This is all I mean. And
P2, sorry, the second moment or
second moment, finite second moments. So there is a change of variables by the gradient of a convex function. And most applications in convex geometry come from this simple fact. Because when you want to deal with volume, you would like to integrate Jacobians. What you would be looking at in this case is determinants of positive semi-definite matrices. So pretty much all the inequalities that the determinants of positive semi-definite matrices satisfy are satisfied by volume. So there is no optimality, this and that needed. It's just this fact that there exists a Brunn map. Super important. And using this, you can prove some functional inequalities like the Prekopa-Leindler inequality and so on, just based on this existence of a Brunn map. Okay. So now, I mentioned earlier that the Wasserstein space is a geodesic space if the underlying x is, and here your geodesics are given by if I have an optimal map P, I will linearly interpolate the optimal map with identity. So of course you can see that at time t is equal to 0, it is identity. So the push forward of mu naught is just mu naught. At time t is equal to 1, it is t. So the push forward is mu1. And this gives you a path from mu naught to mu1. And these are the geodesics in Wasserstein space.
one thing, it is the geodesic only starting from absolutely continuous tensor measures.
Yes. So I think it is, one can do these things about, there could be multiple ones if there is a, you can, yes, I'll just restrict to absolutely continuous finite second moment. Because things of my interest are mainly uniform or uniform type distributions on convex bodies, which will satisfy everything. Now, again, this is the same Newty that we are discussing before. And by this, you can again see for yourself directly that the support of Newty is contained in the Minkowski sum of supports.
That's a mu1.
Yes, mu1. And this is simply because, I mean, at the level of random variables, this is all that is happening. Like if I take a random variable xt, which with distribution mu t, then xt is simply 1 minus t x naught plus t x1, where x naught and x1 are optimally coupled. This is all it is. So you can immediately see from there that the displacement interpolate is contained inside, may not be the full thing, but contained inside the Minkowski sum. And the velocity field that appeared in our picture with gases is just that velocity field which corresponds to this one parameter family of transformations. Now, we have kind of understood what optimal transformation is. We have the Shannon-Boltzmann entropy. And now we had promised to see a proof of the multiplicative form of Brunn Minkowski. So McCann proved that the Shannon-Boltzmann entropy is displacement concave. By displacement concave, I mean that it is concave along the geodesics in the Wasserstein space. So my mu t was the push forward of mu naught under T sub t. Mu t was the push forward under T sub t. And if something is concave along this, I'll call it displacement concave. If something is convex along this, I'll call it displacement convex, and so on. And so this is usually proved. You can prove it using the change of variables that you would get corresponding to this. So this was proved. Such things were proved in bigger, more generality by McCann in his PhD thesis, which was published as a convexity principle for interacting gases. It's a very nice paper to read as an. Yes, we started all of this. Okay. So now, sure, I have this. I just take supremums throughout. Or if you would like, you can plug in the uniform distribution on K0. You can plug in the uniform distribution on K1, and you get something for log volume. To move the logs, you get the multiplicative Brunn Minkowski inequality. So now, how can we get the dimensional form directly? This is a question. Without doing this scaling properties of volume and so on. How can we do it? Using optimal transport. So McCann did this using Renyi entropy, some kind of Renyi entropy, which I don't have to define. So he showed that this is displacement concave, and if you write this out, you will get the dimensional form. But more important for us is this. This was proved by Erbar, Kuwata, and Stun that if you look at exponential entropy over n, this is also displacement concave. So again, now this term was log volume. So this term is volume. So this term is volume to the power 1 over n. So you'll get the same thing, right? The dimensional form of the Brunn Minkowski inequality. And they did this work in, in a very general setting, in metric measure spaces with linear heat flow and many words that I don't understand. But in Euclidean space, the proof is not that bad. If you ever look at our paper, we just write down the Euclidean proof for reference.
With much to the power k is to emphasize the muchness, or
yes, yes. So that it's much more general. So in the language of random vectors, in this language, because xt is just the sum when you take the optimal coupling, what this is saying, and if you use how entropy scales, which again I will not get into, if you multiply by t, entropy comes out as log t. You add log t. Not so important. The point is, this is the same thing as saying e to the entropy over 1 over n and is bigger than this. So one would like to compare it to the Brunn Minkowski inequality. At the same time, many people would like to compare it with the entropy power inequality, which says something similar for the independent coupling. So, and this again is another time when you see that the optimal coupling, optimal transport gives you Brunn Minkowski type things. The independent coupling gives you entropy power inequality type things. So, okay, so this is nice. So now let us see what do I want to do with this. And so if I want to prove something like this, nu is a measure. I want to recall that the Lebesgue measure is 1 over n concave. So I want to approach this question about where is the measure nu alpha concave. And I say the question of global alpha concavity because I ask for all compact sets, K0 and K1, not with any special properties, all compact sets. So this question is kind of well understood at the level of densities, where it was proved by Borel that this is, you can describe this equivalently in terms of the density of nu. This was Borel. And it is implicit in the work of Erbar, Kuwata, and Sturm that you can describe this using a concavity property of the relative entropy. Please note that I have not yet defined relative entropy. But this is the kind of thing that I want to look at. Now, if I have a probability measure here, if nu is a probability measure, I cannot get any alpha concavity for any alpha bigger than 0. First thing, if a probability measure or whatever measure satisfies this for alpha bigger than 0, again by AMGM, it will have to be a log concave measure. It will have to be a log concave measure. And log concave probability measures, log concave probability measures look like this. Unimodal and stuff. They look like this. So if you take K0 to be something with positive measure, take K0 to be something with positive measure, and take K1 to be some singleton, K1 to be a singleton, and send this singleton to infinity. If you send this singleton to infinity, this will get dragged to areas with very low probabilities. This is 0 and this is positive, so it cannot happen. But what I want to discuss mainly is, can it happen if I restrict K0 and K1 to a special class of subsets? Right? The problem here was so it seems from this counter example that you have to somehow be close to the origin if your measure looks like this. This is the kind of thing that I want to approach. So this is the problem. That I have a probability measure. Can I find a large family of compact sets for which there is a dimensional Brunn Minkowski type inequality? Something to mirror what happens for volume. So now I will review some developments that have happened on this thing. So it was shown that there is some big conjecture in convex geometry called the log-Brunn Minkowski conjecture. That conjecture implies that such a thing should hold for all even log concave measures and symmetric convex bodies. K0 and K1 are symmetric, origin symmetric convex bodies. Nu is an even log concave measure. So the log-Brunn Minkowski inequality says that this should hold. But this is why also a lot of convex geometry people are interested in such questions. And the question about 1 over n concavity, this question, for the Gaussian measure was first specifically asked by Gardner and Zowich. And they asked this basically for convex bodies K0 and K1, such that origin is in both of them. But soon after, it was shown that this is not enough, and it was suggested by Nair and Takuch that maybe symmetry is needed here. So note that this is done later. This is 17 and this is like 10 and 12. So this was the question of Gardner and Bromwich. So what did we do since then? So most developments have followed a differential geometric route of directly differentiating what you want to prove. If you want to prove that this thing is concave in T, you can differentiate it twice and you can show that the derivative is negative. So it is much harder than it sounds, and so but you can, it is enough to check here. The Minkowski sum of convex things is always convex, so it is enough to check at time t is equal to 0, and then you can get enough. And this condition at time t is equal to 0 gives a functional inequality for some function on the boundary of the convex body. And then this inequality is transformed into an inequality for functions which are solutions of some elliptic PDE. So this is, I'm just trying to say what is, like what is the other technique here. So you transform this into some inequality about solutions to certain elliptic PDE, and you want to prove it. And in this business, the convexity of K and L is very important. You cannot do anything if K and L are not convex, because at some point you have to take the inverse of the second fundamental form or something like this. That so convexity is super important for this approach. And using this approach, a bunch of things happened. It was proved for a 1/2n concavity result was proved by Kolesnikov and Lifshitz, and this was for all convex K0 and K1 containing the origin. And then Eskenazis and Moschidis used things from the sufficiency criteria that Kolesnikov and Lifshitz came up with in terms of the functional inequality for a solution of a certain elliptic PDE. And they proved 1/n concavity if your K0 and K1 are symmetric convex bodies. So the question of Gardner and Bromwich was settled in this way for the Gaussian. And then Rotem and Cordero-Eraskin, they proved the same result for all rotationally invariant log-concave. So still your K0 and K1 are convex bodies, symmetric convex bodies, because this method depends on the things in the previous slides. And Galina Lifshitz got some result, some dimensional result for all even log concave measures and symmetric convex sets. So this is kind of the most recent result in the direction of the implication of the log Brunn Minkowski conjecture. So there's plenty to do in this direction too, because all these things as late as 1 or 2 years ago are happening on this differential geometric direction. But what we will do is different. We will take a log concave measure. We'll do what we did for volume. We will find the right notion of entropy, which will encode the notion of new measure. We will prove the right displacement concavity property for this notion of entropy. And just as before, the result will follow. So here, instead of differentiating the new measure of convex bodies, we are differentiating entropy, which somehow it seems that this calculus is a little smoother. The calculus on measures is a little smoother than the calculus on convex bodies. So let us define the entropy that is needed. So here is the definition. Nu is a Borel measure on Rn. You can do this in basically any space. And you define the relative entropy of a measure nu with respect to nu by the same formula without a minus. So this is f log f if mu has density f with respect to nu, and you say that it is infinite otherwise. And so this is the definition. So this quantifies how much mu is more spread out than nu. So you want to you are at the level of nu, you are nu, and you see how spread out mu is. So naturally, if you are already the most spread out measure, namely the Lebesgue measure, then the negative of this notion should give you an absolute measure of spread. This is why entropy is an absolute measure of spread, and it is a negative relative entropy from the Lebesgue measure. So now we have our entropy. We do exactly the same thing as before, and last time I wrote a log, so I've just exponentiated things. So I can write the new measure as the supremum of e to the minus relative entropy. And the proof is exactly the same. It's exactly the same proof. But now, use Jensen's inequality. But now, the equality happens as before when the relative density was constant. In the case of entropy, equality happened when the relative density was 1 or something, constant. Here again, you want the relative density to be constant. What does this mean? This means that it is attained by the restriction of the measure nu to the compact set K. So same thing as before. Now our notion of uniform measure has changed a little bit. So now I will outline the general method which we use, which you already have seen, but I'll just write it down on a slide. For summary, I suppose I have a set of probability measures which is closed under interpolations. So that is what I mean by a displacement convex set. I have a set of probability measures. It is closed under the optimal transport interpolations that I do. Suppose fancy K is a class of compact sets, for which all the new K's are inside S. All the achieving of the new measures are inside this set S. And then if you prove that e to the minus alpha relative entropy is a concave function on this set S, that is, if you can prove this, then what you can do is you can plug in the new k0 here to get this, the new k1 here to get this, and you get something here. You don't care about it because it is always contained inside this. So this quantity, whatever it is bounded above by this. So somehow this is also proves things, it refines the geometric inequalities if they're true. But there's something between the volume of the interpolation.
What is nu K? Sorry.
So nu K is the restriction of K to the restriction of nu to K.
Oh.
Which attains the maximum entropy thing. So this is good. This is the most important part. Now, so we want to now apply this to prove things like this. The thing that was in the first slide. That I have the Gaussian measure. I want to prove an inequality like this. So I want to find a set S closed under displacement interpolation, which contains the new case for all star-shaped compact sets, and that displacement concavity of some exponential entropy happens. This is what I want. So now I think I should define what star-shaped compact sets are. So for me, a star-shaped compact set is a set such that containing 0, but such that the ray from the segments from 0 to any other point is completely inside the set. For example, this is far from being convex, but this is star-shaped because this is the origin. I pick any point, the straight line to that point is inside the set. So you can see that the indicator function, because of this picture, the indicator function of a star-shaped set is radially decreasing. You take any direction, it is 1, 1, 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0, 0. So this is a property that indicators are radially decreasing. This will be useful. Okay. So let's prove this. And of course, I'm not going to talk about functional inequalities now because it's like 7-8 minutes left. So let's finish this geometry part. So now I'll take a measure which is log-concave. So it in particular looks like e to the power minus v. V is a convex function. Now I decompose the relative entropy. You can just write it down and this will happen into minus the entropy plus the integral against v. For example, in the Gaussian case, the relative entropy is minus entropy plus the second moment, half the second moment. So you can make this decomposition. Now I want to prove something about this. Elbar, Kawada, and Sturm gave me something about this. So if I prove something about this, I would have a result. Because the geometric mean of concave functions is concave. I don't know what I'll have, but I'll have something. So let me try to get that something. So I can do calculus, as in T. If I have something which looks like e to the minus alpha, some function of t, I want this to be concave, I differentiate twice, and I write down what this means. I just write down what this means. So this should happen. Now, this is what I want to prove. If I want to prove that this is concave. Now, recall the velocity field. So I had my v is simply this. I can just use the continuity equation to find out the derivative of v d mu t. This is what the continuity equation was doing. And then I can use the Hamilton-Jacobi equation to compute the second derivative. These computations are straightforward. So using these things, you calculate these two parts. Now, what do I want? I want to relate this. I want this to be bigger than something times this squared. So it would be useful to somehow relate these two quantities. So I want this to be bigger than alpha this squared. But what is this squared? I just write down the definition. I use some kind of Cauchy-Schwarz. This is just linear algebra. I use some kind of Cauchy-Schwarz. And the second derivative appears. And I have this term. So now I have this is less than this. So I want to prove that this part is less than 1 over alpha. I will not, or you can believe me, like it's late and you don't have to do this. So this is just simple, take the derivative and see what you have to prove. So we see what we have to prove. This is what needs to be proved. And I write this specifically because if you want to, so we have a result for P homogeneous convex functions and so on. But if you can prove this for any measure mu, something like this, on a class of displacement convex measures, then you will have a result. So if P homogeneous, V was the convex function, which was the potential. P homogeneous means that if you have lambda inside, it comes out as lambda to the power 3. For example, the Gaussian measure is, the potential of the Gaussian measure is P homogeneous because you 2 comes out because this is just squared. So if V is P homogeneous, then some calculations become simpler, and you can actually see that the set S of all measures which satisfy this potential energy being less than N over P, this condition of potential energy being less than N over P, is a displacement convex set, and it contains all measures whose density with respect to nu is radially decreasing.
So if n is dimension n or
N is the dimension, yes. N is the dimension, P is the homogeneity of this potential. So the potential energy is less than or equal to N over P. This set is displacement concave and it contains all measures whose density with respect to nu is radially decreasing. So it contains all the nu k's for star-shaped bodies k. And therefore, and I will finish in just about 2 minutes. And therefore, we managed to prove the displacement concavity of, so you don't have to read all of this, just the displacement concavity of this particular thing on the set S. This is what we proved. So now I will put all these things together, and I know this is displacement concave. I know this is displacement concave on S. This is displacement concave on everything, but I only will use it on S. And so I write this down as a geometric mean. Cancellation and multiplication. To show that this is constant. This is constant, and the 1 over P geometric mean will give you exactly this. So this will give you the theorem that the relative entropy to this exponentiated power is displacement concave on S. So by the general method, I plug in the nu k's for star-shaped bodies, and I get this result that V is P homogeneous. For example, the Gaussian measure. Then I get this concavity inequality for star-shaped compact sets K0 and K1.
Gaussian is 2.
Gaussian is 2. So the V is the e to the minus, the thing that appears over here. So this is the result. And as a corollary, you have the result for the Gaussian case. And I wrote down that there is more because I thought I'll do something on the board, but thank you.
Questions?
Are there functions other than powers of measures that can be considered for convexity? So you seem to be raising mu of something to the power.
Yes.
You could go log or something like that.
Yes. So log is zero concavity. Like
Okay.
yeah, log is zero, but you can do it for other things. And there are people who work on such things. I don't know much about this.
And what is the best you can hope for in this? When you follow your strategy, what's the limit is there?
Yes. So if I follow this strategy, of course I cannot do one So the benefit of this thing which I talked about today is that I cannot do the full 1 over n for symmetric convex bodies. So what I can do is I can just relax a little bit on the 1 over n, but I can make the class wider. This is what this part will do. Something else that I did not talk about, which has not done any very concrete things so far, but you can actually approach the problem of 1 over n concavity for symmetric convex bodies using optimal transport. This would be kind of related to the stuff I plan to talk about. But here, star shaped is radially decreasing. The same thing would work there, where a symmetric convex body, if you want to look at the new measure of a symmetric convex body, the corresponding things to look at is that this is log concave and even with respect to the measure nu. So here I had radially decreasing with respect to nu, there I would have log concave and even with respect to nu. And yes. Yes.
Because of that inequality you mentioned.
No. No. So this I use homogeneity. I will show where. I will actually go back. This is, if you do this, you're good. P homogeneity only because this thing simplifies. Yes. But if you prove this, this will be very nice. Yes.
This particular inequality, 1 over 1, that e power that quantity is always concave.
Sorry?
The e power minus ln is concave.
So only potential energy is concave or convex.
Yeah, what is it?
So only this is always displacement convex. This is true. That V that I have defined as integral V d mu, this is equivalent to the convexity of V. But I don't know about this. So this is stronger. Concavity of this by AMGM is stronger than the convexity of this. So it is not clear even if this is.
Many reference like we can Gaussian
Yes.
more general which is more concave.
Yes. Yes. Caffarelli's contraction theorem. So Caffarelli's contraction theorem says that the Brennier map from the Gaussian to anything whose density with respect to the Gaussian is log concave will be one Lipschitz. So this allows you to basically move every functional inequality by every, I mean every in double quotes, to strongly log concave measures. And that is something we use in the second part, which I did not present. Yeah.
Then
In this, like for general radially decreasing or relative log concavity, no, I have no idea. I only know that in some cases, so one very nice proof of Caffarelli's contraction theorem or the existence of a contraction was given by Emanuel Minman and Young-Hon Kim using the heat flow, using Ornstein-Uhlenbeck process. In that, they generalized this to a little bit, actually a wider class of measures. Like instead of the Gaussian, you can look at some more things. But that is, I think, the only thing that I know in a general dimension.
So is there a picopolynder analog of this star?
Very nice question. Again, this is so I initially when I thought that there should be, but we have not been able to do this so far because displacement concavity, the way I find it natural to go from displacement concavity to Prekopa-Lindner is by Donsker-Worthan duality. But that is linear. And here when there is, I have a stronger thing, but I don't yet know how to use it for for getting Pecoppa-Liners. On the other hand, I think that one can use instead, if you could prove these things using the Renier entropy thing, then probably there is some connection of that with, like the generalizations of Pecoppa-Liner, like McPeak, Weinstock, McPeak, like the alpha combination and so on. But not with this. I would be very happy to know if there is something like this.
Also, is there inductive for this? Now that the inequality, there are inductive for this on the lines of Pecoppa-Liner or like,
I don't know. That would actually again be very nice because this will give a third way to approach dimensional Brunn Minkowski type question.
Okay, so if there are no more questions, let's hand over. So before we stop, a couple of announcements. One, the bus tomorrow from CVH will leave at 8:15 in the morning. Since the first talk will begin at 9:15, bus will leave at 8:15. And again, a reminder for sign-up sheets. Okay, please check your emails and you can accordingly decide tomorrow and sign it up. And more importantly, there are snacks outside.
यही बोलेंगे किसी एक ने बोला भी